Hello, everyone. Once again, thank you so much for your time. Today, I'd like to embark on a new topic, which is noise. We are going to take a close look how noise can actually affect a communication system. This video, I'm going to discuss the various sources of noise. We're also going to have a deep discussion on the different types of noise. In short, there are actually two types of noise: external noise and internal noise. Today, this is our objective. We're going to study what are the external noise and also what are the internal noise. This will be the first series discussion on noise. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Please also include your comment how I actually can improve my delivery. Once again, sincere thanks for you guys' support. Thanks again. Let's define what is noise. Noise is any unwanted signal. Noise, in fact, is an undesired effect that they basically either corrupt or distort the transmit signal. Noise actually cause the original signal, either they change in terms of amplitude, there is also some form of delay in terms of time. And also, there are also many possible effects that noise can actually affect the original signal. Noise is a random signal and hence cannot be predicted. I'm not sure whether you're still able to recall when we actually discuss about signal representation, they basically can be classified either periodic or non-periodic. For periodic signal, basically there is so-called some form of pattern that we can predict the signal. But for non-periodics, such as noise, in fact, they are so-called random signal, and hence it almost very difficult to predict. And because of this, we cannot describe noise by any equation. We cannot totally eliminate the noise, but what best we can do is we're going to understand how we can minimize its effect. Noise can be classified into external noise and internal noise, which I have shared with you on the previous slides. For external noise, we have four types of noise. Number one, radiated noise. Number two, power line noise. Number three, atmosphere noise. And number four, space noise. Let's take a close look on radiated noise. The noise is radiated from its generating source, travel through the air, and is being picked up by the nearby radio receiver. Let's take a look on this diagram here. There is a noise source over here. The noise source actually radiate out the noise and basically couple over to the antenna of a radio receiver. And this form of noise is basically classified as radiated noise. The medium is actually the air. Some example of radiated noise are engine ignition system, fluorescent lamp, and etc. Okay, so this actually fall under radiated noise. Next, on power line noise, okay, in the DC and also AC, we have this power line noise. In DC power supply, okay, the 50 Hertz AC ripple can be classified as noise for a receiver that is receiving an extremely weak signal. Okay, so this is actually a DC signal. We actually have a 50 Hertz ripple here. Okay, although this is very small, but when we actually receive a very weak signal, this 50 Hertz ripple can actually have some undesired effect on the weak signal. So this is what we call a power line noise. In AC line, okay, the switching on and off of an inductive load, they basically cause voltage surge. So you can see that there are some form of voltage surge. So this is also can be classified as power line noise. Next, these two are not that significant for external noise. Most of the time, we actually eliminate away Okay, for example, for atmosphere noise, okay, we have some form like lightning discharge. Okay, so this form here, most of the time we will do some EMC in order to ensure our device can withstand this kind of lightning discharge. Okay, other than that, it's almost very difficult to have any form or how can we actually minimize this lightning discharge. We can only ensure that our DUT can survive this kind of lightning discharge. Same wise for space noise, we have this solar noise and cosmic noise. Either they originate from the sun or from the stars. Okay, so again, this kind of noise is almost very difficult to have a form like an equation to govern the noise. Okay, so this is what we have for external noise. For internal noise, it's basically noise that are generated within the receiver itself. Okay, which means that, do you still remember we are discussed about noise in the communication system? So what is called internal noise is basically the noise that they generate within the original receiver itself. The noise is produced by the components. For example, we have noisy resistor, capacitor, inductor, transistor, diode, etc., etc. Okay, so basically these are all those passive devices that capable to generate noise which have undesired effect for the receiver. Okay, every stage of the circuit, they basically will introduce some form of noise, whether a lot or minimum noise. But in short, whatever stage, they basically introduce additional noise. The internal noise that we are going to study is thermal noise. So this is the most dominant noise. Okay, most of the time we only consider this thermal noise. Besides thermal noise, we also have the transistor noise and the frequency dependent noise. As mentioned, this is the most dominant noise for internal noise. How they actually create, okay, because of the thermal interaction between the free electrons and the vibration ion in a conductor. Okay, let's take a quick look on this without going much detail how they actually generate this thermal noise. The random motion of the free electron, where the black dots are the free electrons and the white circle are the positive vibration ion. Okay, so these positive vibration ions, they basically have energy and basically they are vibrating when they actually hit the electron. Basically, this is how we create this thermal noise. Thermal noise spread equally throughout the frequency spectrum. It is also frequency known as either white noise or Johnson noise. The thermal noise is given by this equation. Okay, so this is the thermal noise power. It's basically KTB. K is a Boltzmann constant, which means that this K is a constant number, which is 1.35 times 10 to the power minus 23 joules per K. T is simply the temperature. Okay, we are more familiar on degrees Celsius, but for this case, we need to convert them into Kelvin. So how can we convert into Kelvin? Is simply any form that is in degrees Celsius, we just need to add 273. Anything that is in degrees Celsius, we add 273. This actually convert into temperature in Kelvin. Next, B is basically frequency bandwidth of the system. So this is the formula to compute the noise in the thermal noise. Major noise contribute in transistor is called the short noise. Okay, it is due to the discrete particulars of the electrons and hole in the semiconductor material. Okay, again, let's not take so much look on what is all this short noise. Basically, this is the equation how we can actually quantify the short noise. Is 2Q IDCB. Okay, IN here is basically the short noise. Q is basically a fixed or maybe a constant, which is 1.6 times 10 to the power minus 19 coulombs. This is the DC current, okay, that flow through the transistor. This is the bandwidth or the noise bandwidth. Okay, so this is how we can calculate the short noise on a diode. Next, let's quickly talk about frequency dependent noise. Okay, so the overall noise versus frequency curve for a semiconductor device has a bathtub shape, okay, which means that this is like a bathtub. They have this kind of characteristics when against frequency versus the noise. Okay, later on the first low frequency is dominated by, we call this excessive noise. After that, the noise become quite constant, which is contributed by thermal and shock noise. After that, you can see that there is a sharp increase, okay, which is contributed by the transit time noise. Excessive noise is also called the Freq noise, also called the pink noise, or this is a popular way how we can represent excessive noise, which we call a 1/f noise. Okay, so from this 1/f, we know that it is inverse proportional to the frequency and direct proportional to the temperature. Okay, so this excessive noise, as I mentioned to you, typically they occur at low frequency. So from here, you can see that for this excessive noise, they typically occur below 1 kilohertz. Next, on this transit time noise, okay, so this thermal noise and shock noise I have covered earlier on. So let's focus on this transit time noise. Okay, this transit time noise occur at a higher frequency end, okay, where the transit time of the carrier crossing a junction is comparable to the signal period. So in short, the frequency versus the noise, initial is dominated by the excessive noise. After the frequency increase, the thermal noise and the shock noise become the dominant factor. As the frequency further increase, the transit time noise become the significant factor. With this, I'd like to end the discussion on noise. Please help to support this channel by pressing the like and subscribe button. Once again, thank you so much, guys.